Download this code from codegive.com, link in the description below. OK, let's dive deep into error handling best practices for API requests. This is a crucial area for building robust, reliable, and user-friendly applications. We'll cover various techniques, from handling simple status codes to implementing sophisticated retry mechanisms and logging strategies. I'll include code examples in Python using the requests library, a very common tool for making API calls. But the principles apply to any language or framework. Why error handling matters in API requests. Imagine your application makes a request to an external service, example a payment gateway, a database, a weather API. What happens if the network connection drops? The server is overloaded and returns a 500 error? The API requires authentication, but your credentials are invalid? The API is temporarily unavailable for maintenance. The data you sent is in the wrong format. Without proper error handling, your application could crash or freeze. Display confusing or unhelpful error messages to users. Perform incorrect operations, example double charge a user. Introduce security vulnerabilities. Be difficult to debug and maintain. Effective error handling anticipates these problems, gracefully manages them, and provides a pathway to recovery or resolution. 2. Core principles of error handling. 1. Anticipation. Think about the potential failure points before you write the code. Consider network issues, server problems, data validation, authentication, and rate limiting. 2. Granularity. Handle errors at the appropriate level of detail. Don't just catch a generic exception and display something went wrong. Try to identify the specific cause of the error and handle it accordingly. 3. Graceful degradation. When an API call fails, your application should ideally continue to function in a degraded mode rather than crashing. Perhaps you can use cached data, suggest an alternative action, or temporarily disable a feature. 4. Informative error messages. Display clear, user-friendly error messages that help users understand what went wrong and what they can do about it. Avoid technical jargon. 5. Logging. Record detailed information about errors for debugging and monitoring purposes. Include timestamps, request details, error codes, and stack traces. Use a logging framework instead of just printing to the console. 6. Idempotency. Design your API calls to be idempotent, meaning that repeating the same request multiple times has the same effect as a single request. This is crucial for handling transient errors and retries. This is particularly important when dealing with operations that modify data, example creating or updating resources. 7. Retries. With backoff, implement retry mechanisms to automatically retry failed requests, especially for transient errors like network hiccups or temporary server overloads. Use exponential backoff to avoid overwhelming the server. 8. Circuit breaker. Implement a circuit breaker pattern to prevent repeated attempts to call a failing service, giving it time to recover. 9. Monitoring and alerting. Set up monitoring to track API error rates and trigger alerts when thresholds are exceeded. This allows you to proactively identify and address problems. 3. Common error scenarios and handling techniques. Let's break down some common error scenarios and the best ways to handle them. HTTP status codes. HTTP status codes provide essential information about the outcome of an API request. Here's a breakdown of the common ranges and how to handle them. 2xx, success, the request was successful. 200 OK, 201 created, 204 no content are common. No special error handling is typically needed, but verify the content of the response. *3xx, redirection. The client needs to take additional action to complete the request, example redirecting to a different URL. The requests library usually handles these automatically. *4xx, client error. The client made an error in the request, example invalid data, unauthorized access. *400 bad request, the request was malformed or invalid. Fix the request data. *401 unauthorized, authentication is required but failed. Check your credentials. *403 forbidden, the client doesn't have permission to access the resource. *404 not found, the resource doesn't exist. Check the URL. *405 method not allowed, the resource doesn't support the request method, example using post on a get-only endpoint. *409 conflict, the request conflicts with the current state of the resource. *429 too many requests, the client has exceeded the rate limit. Implement rate limiting and back off. *5xx, server error. The server encountered an error while processing the request. *500 internal server error, a generic server error. Retry the request, or contact the API provider. *502 bad gateway, the server, acting as a gateway or proxy, received an invalid response from another server. *503 service unavailable, the server is temporarily unavailable. Retry the request with backoff. *504 gateway timeout, the server, acting as a gateway or proxy, didn't receive a timely response from another server. B Python code example, requests library. Key improvements and explanations in the example. *logging*. The example now includes a proper logging configuration using the logging module. This is crucial for debugging and monitoring. Logs go to the console, but in a real application, you'd configure logging to write to a file, a database, or a logging service. Use different log levels: debug, info, warning, error, critical, appropriately. *headers*. The make_API_request function now accepts a headers argument, allowing you to set custom headers for the request. This is essential for authentication, content type negotiation, and other API requirements. The post example demonstrates setting content type, application/JSON. *JSON handling. *for post/put requests, the data argument can be a Python dictionary, and the code will automatically serialize it to JSON using JSON equals data in the requests.request call. This is cleaner than manually converting to JSON with JSON.dumps. The code checks if the response is valid JSON using a try, except JSON.JSON decode error block. If the response is supposed to be JSON but isn't, it's logged as a warning, and the raw text is returned instead. This prevents the application from crashing if the API returns unexpected data. *error message handling. The make_API_request function returns a more comprehensive tuple, success, response_data, status_code, error_message. This makes it easier to check for errors and access the response data and error message in the calling code. The calling code always checks the success flag before attempting to use the response data. *timeout. A timeout parameter is added to the make_API_request function. This sets a maximum time, in seconds, to wait for a response from the API. Timeouts are essential to prevent your application from hanging indefinitely if an API server is unresponsive. Asterisk clearer status code handling. Asterisk the code explicitly checks for different status code ranges, 2xx, 4xx, 5xx, and logs appropriate messages. The 429, too many requests, status code is handled with a delay before retrying. Asterisk exception handling. Asterisk the code catches requests.exceptions.request exception to handle common network errors like connection errors, timeouts, DNS resolution failures, and more. This prevents the application from crashing due to network issues. Asterisk retry logic with exponential backoff. Asterisk the make_API_request function implements a retry mechanism with exponential backoff. If a request fails with a retryable error, example 503 service unavailable, 429 too many requests, the code waits for a progressively longer time before retrying, example 1 second, 2 seconds, 4 seconds. This helps to avoid overwhelming the server and increases the chances of success. Asterisk idempotency note. Asterisk the comments highlight the importance of idempotency when dealing with retries. The API operations themselves should be designed to be idempotent if possible. See implementing a circuit breaker. The circuit breaker pattern prevents your application from repeatedly attempting to call a failing service. It works by opening the circuit breaker when the number of failures exceeds a threshold, preventing any further requests until a certain amount of time has passed. After the timeout, the circuit breaker goes into a half-open state, allowing a test request to pass through. If the test request is successful, the circuit breaker is closed and normal operation resumes. Here's a basic example of a circuit breaker class. Explanation of the circuit breaker code. Asterisk states. Asterisk the circuit breaker has 3 states. Asterisk closed, requests are allowed to pass through normally. Asterisk open, requests are blocked to prevent further failures. Asterisk half_open, a test request is allowed to determine if the service has recovered. Asterisk failure_threshold. Asterisk the number of consecutive failures that must occur before the circuit breaker opens. Asterisk recovery_timeout. Asterisk the amount of time, in seconds, to wait before attempting a test request in the half_open state. Asterisk call, func, asterisk args, quargs, asterisk this is the main method that you use to wrap your API calls. It handles the circuit breaker logic. Asterisk record_failure, asterisk increments the failure_count and opens the circuit breaker if the threshold is reached. Asterisk open, asterisk transitions the circuit breaker to the open state. Asterisk reset, asterisk resets the failure_count and transitions the circuit breaker back to the closed state. Asterisk integration. Asterisk the example shows how to integrate the circuit breaker class with your existing make_API_request function. You wrap the API call in a try, except block, and if an exception occurs, the record_failure method is called. The call method manages the state transitions and either executes the API call or blocks it if the circuit is open. 4. Additional best practices. Asterisk rate limiting. Asterisk if you're using an API with rate limits, implement mechanisms to respect those limits. Use the 429 too many requests status code to trigger backoff and retry logic. Consider using a rate limiting library or algorithm. Some APIs provide information about remaining rate limit in the response headers. Asterisk data validation. Asterisk validate the data you're sending to the API to prevent 400 bad request errors. Use schemas, example JSON schema, pedantic, to define the expected data format and validate the data before sending it. Also, validate the data you receive from the API to ensure it's in the expected format and range. *idempotency keys *for APIs that support them, use idempotency keys to ensure that a request is processed only once, even if it's retried multiple times. An idempotency key is a unique identifier that you generate for each request. The API uses this key to track whether the request has already been processed. Asynchronous requests for applications that need to make many API requests concurrently, consider using asynchronous requests, example with asyncio and iotp in Python. This can improve performance and responsiveness. Caching cache API responses to reduce the number of requests to the API. Use appropriate caching strategies, example expiration, invalidation, to ensure that the cached data is up to date. Monitoring and alerting use monitoring tools, example Prometheus, Grafana, Datadog, to track API error rates, response times, and other metrics. Set up alerts to notify you when problems occur. API wrappers / SDKs if the API provider offers an SDK or wrapper library, use it. These libraries often provide built-in error handling, retry logic, and other features that can simplify your code. Documentation clearly document your error handling strategy in your code and documentation. This will make it easier for others to understand and maintain your code. Conclusion. Robust error handling is essential for building reliable and resilient applications that interact with APIs. By anticipating potential errors, handling them gracefully, logging detailed information, implementing retry mechanisms, and using patterns like the circuit breaker, you can significantly improve the quality and stability of your applications. Remember that error handling is an ongoing process, and you should continuously monitor your applications and adjust your error handling strategy as needed. The example code provides a solid foundation, but you'll need to adapt it to the specific requirements of your application and the APIs you're using.